Okay, me again. So let's go over the second part of chapter 12. So let me share the screen first. All right, here is the document camera. Okay, so the first part we had discussion on the shear stress, which is this tau is equal to VQ over IT. So whenever we have a shear force, we should be able to find out the corresponding shear stress using this equation, right? The other concept in the last part of the chapter 12 is shear flow. So shear flow Q, we can calculate it as VQ over I. So this is, the definition is this is shear force per unit length. So in your textbook, in page, let's see, in page 578, you can read the description in chapter 12.3, shear flow in built-up sections. And one of the reasons why we need to calculate the shear flow is because think about the built-up section. Built-up section, we build up section with some parts and attach those parts together through either glue or the nails. And we have to have an understanding about how much force is going to be applied to this member so that we can determine how many nails are required or how strong the glue is going to be required to these sections, right? So that's how we can apply this concept of shear flow into real world problems. So we're going to talk more about this through the example 12.4. So here's example 12.4. The problem is this: we have a built-up section. So, and that beam is constructed from 3 boards glued together, and it looks something like this. I'm going to draw it here. So this is the top board, and then 2 other boards here. Okay, so something like this. Okay, so this beam is constructed from 3 boards glued together, and it is subjected to a shear force of 850 kilonewton. This is also a SI unit. Then we'd like to know, determine the shear flow at these 2 points. So this is point B, this is B prime. So we'd like to know the shear flow at B and B prime that must be resisted by the glue, right? So again, one of the application that we can use this shear flow concept is that when we build up a section, we can determine how much force is going to be required for our glue or any other the ways of the connections like nails or something like that. Okay, the dimensions are the top flange portion, the thickness is 10 in millimeter. The entire width is 250 in millimeter. And then this is also 10. The length of these legs are different, is 300 millimeter. The distance between these 2 legs is given as 125 in millimeter. So those are all given information. So first of all, in this case, we have to have an understanding, we have to identify the location of centroid for the entire section. Color. So let's say here is the centroid of the entire section, then it is going to be the neutral axis, right? So we have to find out the distance either from the top or the bottom. I'm going to just measure from the bottom. So let's say this is y bar. So the first step is we have to find out the location of centroid for the entire section. And that is, you all know that y bar is going to be equal to y bar times a divided by sum of a. So we have three different areas. So we're going to find out the y bar for each one of them, measuring from the bottom, and then multiply by cross-sectional area for each board, and then divided by the sum of the entire areas. So I'm going to use just red pen. Okay, so let's look at the top flange. The location of center of this top board is here, so that we can measure the distance from the bottom to that location is going to be 300 millimeter plus 10 divided by 2, which is 5 millimeters. So entire length is going to be 305, right? So I'm going to convert everything into in meter. So it is going to be 0.305 times the area is going to be 250 in millimeter times 10 in millimeter. It's going to be 0.25 times 0.01. Okay, and then we have to have, this is all in the numerator. We have to add these two legs, okay? And those are identical, so I'm going to just multiply by 2 to the distance from the bottom to the location of center is 1/2. I mean, the 1/2 of 300 millimeters, so it's going to be 0.15 times the area of this leg. Each one is going to be 300 millimeter times 10. It's going to be 0.3, 0.01, and then multiply by 2 that include both legs. Okay, so this is the all in the numerator divided by the areas, the sum of the areas, which is 0.25 times 0.01 plus twice of 0.3 times 0.01. Okay, so this is numerator, this is denominator. When you calculate it, I got 0.1956. Everything is in meter. So that is the distance from the bottom of the section to the location of centroid of the entire section. So this is the first step. The second step, the reason that we have to know the centroid of the entire section is because, remember, this Q calculation and even I calculation, we have to understand, we have to know the location of centroid for the entire section, right? That's why I started with this centroid calculation. The next step is going to be this V, because V is already given as 850 kilonewton, so that's a constant already. So let's calculate the moment of inertia for this section. Okay, so the moment of inertia, I'm going to use a blue pen. Moment of inertia I, we can calculate it as the summation of I prime plus a d square using parallel axis theorem, right? So I prime is the moment of inertia about its own centroidal axis, right? Here. And then add AD squared terms for each one of them, which is the area of each one. And D is going to be the distance from this neutral axis of the entire section to its centroidal axis. So let's do that. So I'm going to start with the top one, which is I prime is going to be BH cubed over 12. So 0.25, H is 0.01 cubic over 12 plus area 0.25 times 0.01. And D is going to be the distance from here to here, right? Since now y bar is 0.1956, and the distance from the bottom to this location was 305 millimeters, so 0.305. So D is going to be, this distance is going to be 0.305 minus 0.1956. Okay, so 0.305 minus 0.1956 squared. So this is the moment of inertia for this top flange about this axis. Plus, we're going to add the moment of inertia for each one of these about this new axis. And these are the identical, so I'm going to multiply by 2 for all the calculation. So 2 times BH cubed over 12. So B now is going to be 0.1, 0.1. No, the 0.01, sorry, 0.01 times H is 0.3 cubic over 12 plus area 0.01 times 0.3, and now D. D is kind of the distance between these two, right? From bottom to the location of centroid for the entire section was 195.6 in millimeter. Distance from the bottom to the center of this lag is 150, which is 1/2 of 300. So this is going to be what? 0.1956 minus 0.15, right? So it's going to be 0.1956 minus 0.15 squared. So when you calculate this moment of inertia, I got 87.42 times 10 to negative 6, and everything is in meters, so meter to the 4th. Sounds good? All right, I'm gonna go on to the next page. So what we were looking for was the Q, small q. Small q again is VQ over I. So we have the shear force, which is given as 850 in kilonewton. And the moment of inertia, we just calculated as 87.42 times 10 to negative 6 in meter to the 4th. This is 850 in kilonewtons, so I can say 850 times 10 to 3 in newtons. So I'm going to convert everything into newton and meter units. The only thing left is this Q. And again, Q is a first moment of an area. And we can calculate Q as Y bar times A prime. So Y bar is going to be the distance from the neutral axis of the entire section to the area that we're going to considering. So let me go back to this figure and talking about A and Y, right? So B and B primes are here, and we are always measuring the kind of estimating the area from the top of the section. So from the top up to this point, the corresponding area is going to be this shaded area. So you can easily find out the area as 250 millimeter times 10 in millimeter. Now, the distance Y bar is from this neutral axis to the center of this shaded area, which is this. Again, we already calculated that as 0.305 minus 0.1956 in meter. So those two numbers are going to be used in our first moment of area, the Q calculation. So here we go. So Y bar was 0.305 minus 0.1956. And then area A prime was the area of the top flange, which is 0.25, 250 in millimeter times 0.01, 10 in millimeter. When I calculate Q, it is going to be 0.2735 times 10 to negative 3. Look at the unit for Q. Q is, again, the first moment of an area. Area times the distance. Area, we have meter square unit. Distance is a meter unit, so it is going to be in meter cubic. Okay, so that's everything. So I'm going to just substitute it into this Q and then calculate this small q shear flow. So that is 850 times 10 to 3 in Newton. So that's V. Q is this, 0.2735, 10 to negative 3. 10 to negative 3, 10 to 3 is already canceled out. And this is the meter cubic. And 87.42 times 10 to negative 6 meter to the fourth. So it is meter cubic, and this is Newton. So we only have 1 meter unit left with Newton per meter, which makes sense. And then 10 to 3 and 10 to negative 3s are canceled out. And we have 10 to negative 6 in the denominator. So it's going to be 10 to 6, right? Which is mega. So when I simplify this calculation, I got 2.66 in mega Newton per meter. So again, the shear flow, the unit will be force unit divided by the length unit because of, remember the definition of shear flow. Shear flow is a shear force per unit length, right? And this mega is coming from 10 to 6. Now, this is not the end because this is the shear flow at the bottom of the top flange. So let me go back to the figure again. So here's a figure, and that is the shear flow at the bottom level here. And the shear flow at each point, B and B prime, it is depending on how many sims we have. If we have 5 legs versus 2 legs versus 1 leg, we have to have a different level of shear flow because we have, different number of elements to take care of that shear, the shear force per unit length. Does that make sense? So in this case, because we have 2 sims, 2 legs, we have to divide it by 2 for that given shear flow. So here we have a shear flow 2.66 mega Newton per meter. So the Q at B will be equal to Q at B prime, which is this entire Q divided by 2. So the final answer is going to be 1.33 mega Newton per meter. Looks good? All right. So that is example 12.4. If you have any questions on this or the other example problem 12.3, just let me know. And this is the last part of this is the last part of the chapter 12. So in the next video, I'm going to go over chapter 13, which is going to be very short because we already had the first half of the chapter 13 covered at the end of chapter 10. No, chapter 11, sorry. When we talk about the bending stress, we already talked about the unsymmetric bending, which was really, really complicated example problems. You may remember that in the new textbook, in the new organization, they just moved that unsymmetric bending into the combined loading section, which is chapter 13. So I'm gonna skip that part and then just focus on the last half, which is the stress for the spherical vessel, or the cylindrical vessel, the container. So that's all. All right, so you expect to have one more video clip for chapter 13 for this week. And by the way, I'm gonna post another entertainment package, right? Even though we cannot meet together, we have to entertain ourselves too, right? So I'm gonna post the entertainment package for chapter 12 sometime today so that you can enjoy the entertainment package. All right, that's all. Thank you. See you later.